Evaporation and condensation. Intermolecular force strength comes into this as well. So here you are, I'm answering your question. So evaporation, vaporization, those terms mean the same thing. It's the change in state from liquid to a gas. The rate of evaporation or vaporization increases with increasing surface area, with increasing temperature, and with decreasing strength of intermolecular forces. So let's think about water. You have maybe a tablespoon of water and you want it to evaporate. If we increase the surface area, it will evaporate faster, won't it? If we leave it sitting in a little tablespoon that we measured it in, the surface area is small. If we take that water and we spread it out on the counter and increase the surface area, it will evaporate more quickly, right? That's one of the reasons that when you're drying your hands on under one of those annoying hand dryers in one of those annoying bathrooms that doesn't have any paper towels, what do? You just hold your hands there with water cupped in them? No, you rub them together, right? Because that spreads the water around on your hand and increases the surface area. Why do we blow warm air on our hands instead of cold air? Not just because it feels nice. It dries faster at a higher temperature. Water evaporates faster at a high temperature. So think of the sidewalk in January and the sidewalk in July. And you take a cup of water and you pour it on the sidewalk. Is it going to evaporate faster in January or in July? July. In July, you can watch it evaporate because you could almost fry an egg on that sidewalk. Almost. On the blacktop, you probably could, but not on the white sidewalk. That's another thing. But in January, when the sidewalk is cold, the water will evaporate, but it'll take a lot longer. Intermolecular forces have a process in this as well. The stronger the intermolecular forces, the longer it takes to evaporate. Does cooking oil evaporate? In theory, it could eventually evaporate, but in practice, it doesn't, right? You spill a little vegetable oil on the counter and you come back 3 days later and it's just still sitting there. You spill an equal amount of water on the counter, though, and it's going to be gone within a couple hours at least, right? It'll just dry up. It evaporates into the air. Water has stronger intermolecular force. Well, that's not a good analogy, but never mind, back up. Liquids that are volatile evaporate easily. Non-volatile means it does not vaporize easily. Things like gasoline and alcohol are volatile. Acetone, fingernail polish remover, paint thinner, all of those things are considered volatile. Cooking oil is non-volatile. So let's look at evaporation. So here we have our water molecules, and they would be moving around. They're jiggling and they're moving next to each other. And they have an average kinetic energy based on their temperature, but they're not all at the same kinetic energy. Some of them are moving quickly, some of them are moving slowly. The average depends on the temperature. So we've got some fast ones, and we've got some really slow ones, and they're moving in different directions. So if we have a fast-moving particle that heads towards the surface, it can have enough energy to break free from the surrounding molecules and get into the gas state. So this is water molecules playing Red Rover. You guys know what Red Rover is? I don't think they let kids play that in elementary school anymore because they're worried that people are going to get hurt. Pretty soon they're going to ban running, right? And then they're complaining about how children are not getting enough exercise. Well, make up your mind. But Red Rover, in case you don't know, kids make a line and they hold hands, and then you've got other kids standing across the field, And the kids on the line say, Red Rover, send Susie right over, right? And Susie runs as fast as she can, and she's trying to break through their arms, right? Break through the hands. So you can imagine how people could get hurt. But, you know, if you're that fragile, then maybe you shouldn't be playing games. So this is the Red Rover line. How tightly those kids are holding hands is a measure of the strength of the intermolecular forces. Okay? So, if you've got the O-line of the COS football team as your Red Rover line, or you've got the kindergarten class as the Red Rover line, there's going to be a difference in how fast you have to run to get through, right? So, if the intermolecular forces are weak, if the Red Rover line is weak, almost anybody can get out. Almost anybody can get through. And so the particles will evaporate quickly. If the Red Rover line is really strong, then only the really fast kids are going to be able to break through. And so very little evaporation will happen. What else can you do to speed up evaporation? We talked about it. If we increase the temperature of this, what happens to the average speed of the molecules? It increases. So now everybody's running faster, more of them are going to be able to break loose. You can only break loose if you're running at the surface, right? So if we doubled the surface area, there would be twice as many molecules that would be able to break free because there's more surface area. You can run around all you want down here, you're not going to get into the gas state. You have to run towards the surface. And so more surface area means there's more particles at the surface and more of them can escape. So intermolecular forces have a lot to do with the rate of evaporation. Any questions? So this is a diagram showing fraction of molecules with a particular amount of energy versus kinetic energy. So at a low temperature, the average kinetic energy would be about in here somewhere. And if you're in calculus, you could tell me all about that. If we increase the temperature, the average kinetic energy will increase. But here is the minimum kinetic energy needed to escape from that liquid. And so at a low temperature, it's just the area under the curve here. These are the particles that have enough energy to get out. As we increase the temperature, not only does the average energy increase, but we also see this spread, and so you've got this wider range. And so that curve gets shorter and wider, and we see at a higher temperature, we've got a lot more particles that are able to escape. So increasing the temperature increases the number of particles that have enough energy to get out. Condensation is the opposite process of evaporation. This is where something goes from the gas state to the liquid state. You can have a dynamic equilibrium between evaporation and condensation. If you think about, well, I think we've got a picture coming up, hopefully. In a dynamic equilibrium, the number of gas molecules remains constant. And so you've got gas above the liquid, gases exert pressures, and so we call that the vapor pressure. So let's look at this. So here we have an Erlenmeyer flask with a stopper, and we've got some water in the bottom. Now initially, there wasn't any water vapor, no water in the gas state. But as this water is sitting here, it's playing Red Rover, and some of the particles are going to escape into the gas state. And that's going to go on at a constant rate. So gas particles are going to escape. Yeah, well, water molecules will escape into the gas state. So what do these gas particles do? They just float above the water and just sit there? These guys are zinging around like a game of Pong. Do you remember Pong? It was like the first video game. It was awesome at the time. We were just so amazed. It was this little blip, and it would bounce around, and then you had a paddle at the bottom, and you had to move the paddle so that it would hit the paddle and keep bouncing. And we were just transfixed by this. It's amazing. People can get so just fascinated with the dumbest things. So I imagine these like the little blip on Pong, and it bounces around, and eventually it's going to hit the surface of the water. There's no paddle here. When it hits the surface, it gets trapped. It gets sucked back in because it's like splashing down, and it's like all these other water molecules are like, hey, you came back to us. And it just sticks to it like Velcro. So the water molecules evaporate, they bounce around, eventually they start to condense. Just randomly, because they're floating around randomly, and they will eventually hit the surface.
This is room temperature?
This is room temperature. So you get some condensation occurring. The more water you have in the gas state, the more condensation you will have, right? Because the rate of that depends on the concentration of this gas. More gas particles up here, more are going to collide with the surface and get trapped. The rate of evaporation in the meantime is just staying the same. Eventually what will happen is that the rate of evaporation and the rate of condensation become equal. And that's where we get an equilibrium. We have liquid molecules escaping into the gas state at the same rate that gas particles are being trapped back into the liquid. So even though there's this constant exchange of molecules, the number of molecules in the gas state remains constant. It's different molecules all the time, but the number is the same. Those gas particles are going to exert a pressure, and we call that the vapor pressure. So remember we talked about Dalton's law of partial pressures, and we said when we did that experiment with the eudiometer and we collected the gas over water, well, this happened in the top of your eudiometer. The water in the eudiometer became in equilibrium with water in the gas state above it. And the vapor pressure here of the water depends only on the temperature. If I increase the temperature of the water, what does that do to the rate of evaporation? It increases it. I get more gas particles. So I'll get more and more up here, and then as more and more get up here, the rate of condensation will also increase, but the net result is more gas particles. So at higher temperatures, the vapor pressure is higher. At lower temperatures, the vapor pressure is lower. Question?
Well, it's not, you said when it hits the surface,
It gets
the
trapped.
condensation happens when it's trapped, but it also happens on the sides and so.
Condensation can also happen on the sides of the container. That will happen when the sides of the container are cool. Condensation happens on cold things, right? You pull a can of soda out of a refrigerator on a hot day. It's not as obvious around here because it's so arid. The humidity is so low. But on one of those rare humid days, the outside of the can gets wet, right? Or you've got a glass of ice water and the outside gets wet. We say it's sweating. Where's that water coming from? Is the can leaking? No. You've got a cold surface and you've got water in the air in the gas state. When it hits that cold surface, the cold surface causes the temperature of the water to go down and it will condense because of the cold. So in this situation, we could have condensation on the sides depending on how cold it is outside of this flask. But even if it did, you're going to have evaporation and condensation into those little drops, and you're still going to come to the same equilibrium vapor pressure. Any other questions? So vapor pressure will increase with increasing temperature, and it also increases with decreasing strength of intermolecular forces. If the stick-togetherness of the molecules is lower, if the red rover line is the kindergartners, the rate of evaporation is greater, and you'll end up with more gas particles. If the intermolecular forces are strong, it's the football players this time. Not as many can get out, and so the number of particles in the gas state will be smaller. Vapor pressure does not depend on surface area. The rate of evaporation depends on surface area, but the rate of condensation also depends on surface area. And so the effect of surface area basically cancels out. If you have a container where the surface area of the water is much larger, you're going to have the same vapor pressure. Because even though the rate of evaporation increases, with a larger surface area, more of those gas particles are going to run into it, and so the rate of condensation will be affected equally. What happens when something boils? We said vapor pressure increases with increasing temperature. Think of taking some water. There's a pot of water. And as you increase the temperature, you heat it on the stove, the vapor pressure would increase and increase and increase. You couldn't measure the vapor pressure in this pot, though, because it's open. You can only measure vapor pressure in a closed container. But as we heat this up, the vapor pressure gets higher and higher and higher. When we get to the boiling point of the liquid, there's enough thermal energy that the water molecules inside the surface of the liquid can become gas. And that's why we see bubbles forming. You see little bubbles of water vapor forming within the liquid. And you see the bubbles, and of course bubbles being less dense, rise up to the surface and pop. But that's why there are bubbles in water when it's boiling. Once we get to that boiling point, you can heat it more and more and more, but the temperature of the water does not increase. So let's go back to this picture because I like pictures. Remember we said there's a variation in the kinetic energy of the different water particles. As you increase the temperature, you increase the average kinetic energy, but you've still got slow ones and fast ones. Which ones are going into the gas state? The fast ones or the slow ones? The fast ones, the ones with more energy. The ones with more energy make these bubbles and they go to the surface and they escape. So we're putting heat in, but all the high energy particles are escaping. That keeps the average kinetic energy at the same point. It can't go above 100 degrees Celsius until all the particles have turned into a gas state. And at that point, the temperature will shoot up rapidly. And that's where, oh, you forgot the pot of water on the stove. And it's all good until the last drop of water evaporates, and then the pan starts to burn and smell nasty, right? The water temperature stays the same until all the particles have evaporated. So you're making spaghetti. As soon as the water comes to a nice rolling boil, you might as well put the spaghetti in there. Waiting another 10 minutes, the water is not going to get any hotter. So what we see happening is that as you increase the as you add heat to water, the temperature will increase. And that makes sense to us. Once it starts to boil, though, the temperature will stay the same until all the water has evaporated. And then the steam can increase in temperature. But water at the boiling point is always going to be 100 degrees Celsius. And we'll pick this up next week.